Is there something faster than the speed of light? The official answer is no, but the real story is much more complicated and fascinating. To understand it, we need to go back to a legendary showdown between two of science's greatest minds, Albert Einstein and Niels Bohr. For centuries, the idea of action at a distance has been a scientific puzzle. Even Isaac Newton was bothered by his own theory of gravity, which seemed to suggest that the Earth instantly knows where the sun is. How could that signal travel across space instantaneously? He called it an absurdity but had no better explanation. Then, Einstein came along. His theory of relativity solved Newton's problem by showing that gravity isn't an instant force. Instead, it's a disturbance in spacetime that travels at the speed of light. This established a universal speed limit. Nothing, Einstein declared, could travel faster than light. This wasn't just a rule. It was a fundamental principle ensuring that cause always precedes effect for all observers. This principle is called locality, but a new theory was emerging that seemed to break this very rule: quantum mechanics, and Einstein was not a fan. At the famous 1927 Solvay conference, he went head-to-head with Niels Bohr, the champion of the new quantum theory. Einstein's main objection was that quantum mechanics seemed to violate locality. Here's why. According to the standard interpretation of quantum mechanics, championed by Bohr and known as the Copenhagen Interpretation, particles don't have definite properties until they are measured. Before that, they exist in a superposition of all possible states, described by something called a wave function. When you measure the particle, its wave function instantly collapses into a single, definite state. Einstein argued that if this wave function is spread out over a large area, its collapse everywhere at once would mean some kind of influence is traveling faster than light. Bohr's response was essentially, that's just how it is. He argued that the wave function isn't a physical wave, but simply a mathematical tool that describes everything we can possibly know about a system. The debate was about the very nature of reality. Is there a real, objective world out there, independent of our observations, as Einstein believed? Or is reality created, in a sense, by the act of measurement, as Bohr suggested? Einstein was convinced that quantum mechanics was incomplete. He believed there must be some deeper reality that the theory wasn't accounting for. In 1935, he, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper outlining a thought experiment that would become legendary: the PR paradox. Imagine you create a pair of particles that are entangled. This means their fates are linked, no matter how far apart they are. For example, if you have two entangled electrons, their spins will always be opposite. If you measure one and find its spin is up, you instantly know the other's spin is down, even if it's on the other side of the galaxy. To Einstein, this was proof that quantum mechanics was incomplete. How could the measurement of one particle instantly affect the other one light years away? He called it spooky action at a distance. He proposed that the particles weren't communicating faster than light at all. Instead, they must have had their properties, their spins determined from the moment they were created. He suggested there were local hidden variables, like little instruction sets inside each particle, telling them how to behave when measured. In this view, measuring one particle doesn't influence the other. It just reveals a pre-existing property that was always there. It's like opening one of two envelopes to find a red card. You instantly know the other contains a black card, not because you changed it, but because they were set up that way from the start. For decades, this was a philosophical debate. Einstein's hidden variables or Bohr's spooky action. There seemed to be no way to test which was right. The predictions for a single pair of entangled particles were identical in both theories. Then, in the 1960s, a physicist named John Bell had a breakthrough. He realized that while the theories gave the same predictions for perfectly aligned measurements, they would give different predictions if the measurements were made at different angles. Bell devised a mathematical theorem, now called Bell's theorem, that set a limit on how much two entangled particles could disagree if Einstein's local hidden variables were real. Here's the core idea. Imagine you and a friend are measuring the spins of many pairs of entangled particles. You each have a detector that can be set to 3 different angles. Sometimes your detectors will be at the same angle, and you'll always get opposite results, perfect agreement. But what about when your detectors are at different angles? If Einstein was right and the particles had predetermined instructions, Bell calculated that your results should disagree at least 33% of the time. However, if Bohr was right and quantum mechanics is correct, the disagreement rate should only be 25%. This small but crucial difference meant that the debate was no longer just philosophical. It could be settled by an experiment. In the 1980s, a French physicist named Alain Aspect and his team performed this very experiment, known as a Bell test. They created thousands of entangled photons and set them in opposite directions to detectors that could be switched to different angles at the last nanosecond. This was critical to ensure there was no way the detectors could somehow communicate with each other. The results were stunning and unambiguous. Time and time again, the experiments showed a disagreement rate of 25%, exactly as predicted by quantum mechanics. The 33% limit set by Bell's theorem for local realism was clearly violated. Einstein, it seemed, was wrong. So, what does this mean? It means that our universe is non-local. Spooky action at a distance is real. Measuring one particle really does seem to have an instantaneous effect on its entangled partner, no matter the distance. Yes, something is happening that is faster than light. But hold on, does this mean we can build a faster-than-light telephone and call another galaxy? Unfortunately, no. While the influence is instantaneous, we can't use it to send a message. The reason is the inherent randomness of quantum mechanics. When you measure your particle, you can't choose whether you get spin up or spin down. It's completely random. You find out the state of the distant particle instantly, but you can't control it to send a coded message. Your friend on the other end just sees a random sequence of ups and downs, and only by comparing your results later using normal, slower-than-light communication can you both see the spooky correlation. The proof of non-locality has profound implications, forcing us to rethink the nature of space and reality itself. But it doesn't get rid of the weirdness of the wave function collapse. Some physicists, still uncomfortable with this idea, have proposed alternative interpretations. One of the most mind-bending is the many worlds interpretation. It suggests that the wave function never collapses at all. Instead, every time a quantum measurement is made, the universe splits. In one universe, you measure spin-up, and in another, parallel universe, a copy of you measures spin-down. All possible outcomes happen, each in its own separate branch of reality. In this view, there's no spooky action because there's no collapse. The correlation between entangled particles exists across these different branches. The version of you who sees spin-up exists in a branch where the distant particle is spin down, and that was simply the way this branch of the universe split. So, while we can send messages faster than light, the universe does seem to possess a hidden, instantaneous connection that defies our everyday intuition. The legacy of the Einstein-Bohr debate is the realization that reality is far stranger than we ever imagined. Whether you prefer a single universe with spooky connections or an infinite number of parallel worlds, one thing is certain: the universe is not as local as it seems. Thank you for watching. If you enjoyed this journey into the quantum world, don't forget to like and subscribe for more deep dives into the mysteries of science.